Welcome back. So this is our third video on area and finding the distance traveled by using area. And this video is kind of a summary of our first two examples, and then we're going to do another example together. So on an increasing function, so we're talking an increasing function, the lower sum is the same as the left-hand sum, or the left endpoints, if you will. In other words, when computing the lower sum, we actually use the left-hand endpoints of each interval to compute the height of each rectangle. The upper sum is the same as the right-hand sum. In other words, when computing the upper sum, we are actually using the right-hand endpoints of each interval to compute the height of each rectangle. So an increasing function, the left-hand sum is actually less than or equal to the actual value, which is less than or equal to the right-hand sum. So this basically here is our lower estimate, and this is our upper estimate because it's an increasing function. So the underestimate is our left-hand sum, and our overestimate is our right-hand sum. Okay? Notice on a decreasing function, the lower sum is actually the right-hand sum because it's a decreasing function. In other words, when computing the lower sum, we are actually using the right-hand endpoint of each interval to compute the height of the rectangle. The upper sum is actually the left-hand sum. In other words, when computing the upper sum, we are actually using the left-hand endpoint of each interval to compute the height of the rectangle. In this case, the left-hand sum is greater than or equal to the actual value, which is greater than or equal to the right-hand sum. This is our underestimate, and this is our overestimate. So our underestimate is going to be our right-hand sum, and our overestimate is going to be our left-hand sum. They're opposite. All right? So, a couple other things we learned. We learned interval length. So our interval length, which is our delta t, what we did to find that out is we actually did this formula, b minus a all over n, and let's label everything. So delta t is our interval length. That was basically how wide our rectangles were. A is our start time. B is our end time. And n was the number of subdivisions. Excuse me. And when we first started out, I said, oh, this is the number of rectangles we have, which it is. It's the number of subdivisions. So in order to find the interval length and the start end time and the number of subdivisions, sometimes you're given some of this information. Now if you'll notice, I actually gave you a table the first couple of examples, but now we don't need to know the tables. We can come up with our own table to do this, all right, using that formula. So this is an important formula that you know this. Delta t is b minus a over n, okay? All right, so let's do an example, and we will use that formula. This says, suppose the velocity of a car is given by v of t equals 65 cosine 0.1 t, and our time is between 0 and 12. Okay, so this is our beginning time. So this is our, oops, sorry, I didn't mean to hit that. Let's go back. This is our beginning time, or a, and this is our end time, b. They told us they want us to take it every 3 seconds, all right? They said find the upper and lower estimates for the distance traveled. Now, first of all, this information is enough so you can make your own table. And you can also just put this in your calculator and set up your table with 3, and you would have your points right off the bat. So we know that delta t is 3. We know that delta t is b minus a all over n. And this will tell you how many subdivisions are rectangles. So I'm going to put the 3 in for here. I'm going to end of 12, start with 0 over n. And so basically, you're going to, when you solve this, you have n comes out to be 4. So I'm going to have 4 subdivisions or 4 rectangles. Now, If I have 4 subdivisions or 4 rectangles, remember you're going to have 5 columns in your table because you have to have a starting point. Now, if you put this in your graphing calculator, your table goes vertically, but we're going to go horizontally because that's what we're used to. All right, so, and I'm actually going to make 6 columns because I have to have a label. Okay, so we're going to do 1, 2, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And this is hours. So this is hours we're talking about. And this is going to be our velocity. So it's going to be like miles per hour or whatever we're going to do here. And we're going to start at 0 and we're going to be counting by 3. So it's going to be 3, 6, 9, 12. And when to put this in here, if you put this in your calculator right here, the 65 cosine, make sure you're in radians, and you check your table, all we're going to do is write down what the value is. So at 0 it's 65, at 3 it's 62.1, at 6 it's 53.6, and then it's 40.4, and 23.6. Okay, now I want you to notice that this function is decreasing. This car is slowing down, all right, between 0 and 12 seconds, all right? So if I want to do the upper sum, it would have to be the left-hand sum, and the lower sum would be the right-hand sum, just because it's a decreasing function. So my upper sum is going to be the left-hand sum, or using my left endpoints. And I'm going to take the interval that I'm using, which is 3, and I'm going to start from here, and I'm going to go to here and use that. So I got 65 plus 62.1 plus 53.6 plus 40.4. That comes out to be 663.3 miles. Okay. My lower sum is my right-hand sum in this case. So I'm going to start here at the 62.1. I'm going to end at the 23.6. So it's still 3 hours every time I'm doing this. So it's 62.1 plus 53.6 plus 40.4 plus 23.6. When I do that, I have 539.1 miles. All right. And if I asked you, okay, do you think would be a good guess? I would add them up, divide by 2, and that would be my good guess. All right. So here's one where they didn't give us the tables, but we can come up with it ourselves using this formula of delta t b minus a, and as long as you have what that is, you can fill out your own table and make a good guess, all right, of what the distance traveled is. Now, this next one is also a summarization. We're going to talk about the general Riemann sum. And this is just, I want to show you the background of how we come up with how we're doing the area under the curve. So it says in our last example, suppose we want to divide the interval into 6 intervals. How big would each interval be? Well, again, you're going to need to know your beginning and your end. And we call that A and B. And if you'll notice, they use x sub 0 and then they use x sub n as our end, and then see how it's n minus 1. So this is just notation on how you can label things, and these are all our intervals right here. So I have an interval right here, interval, get the idea? These are all the intervals that we made. Now, here is our formula. Delta x is b minus a over n, so you can figure out how many you're going to do. Let's look at how you would determine expression with the left-hand sum. Well, basically with the left-hand sum, we start with the function or the y value of the left, which is x sub 0, and we end one short. Okay? Now notice they have this delta x because you're multiplying it. This is basically right here, the width. This is your x value. So this is the width of your rectangle. And this is the height, which is the y value of your rectangle, and then we're multiplying it all, and we're stopping one short. See the x to n minus 1? So the left-hand sum this is the summation from 0 to 1 short of all my y values times that change in my x. All right, so this is using the summation. This basically, just for a little background, is the Greek symbol for sum, and it's the Greek letter S, all right, capital S. The right-hand sum is we're doing the same thing, except we're starting at the first value. See here how we start at 0, we're starting 1 over, and we're ending at the end, which is the sum of x sub 1 times the delta x, so that shows you how you're doing the sum of all these rectangles, but you're starting at the first one and ending at the very end. Again, that's the Greek letter of adding all this up. What is this leading to? Well, this is what it's leading to. The limit as n goes to infinity. So if I were to take this and put a limit in front of it, I'm basically saying if I keep increasing the number of rectangles infinitely, as n gets larger and larger and larger. So I'm increasing the number of rectangles so that they're smaller and smaller and smaller and smaller and smaller. It's going to get closer and closer to what that curve is going to be, and you're going to get a better estimate. Is they switched over from the limit is now you're using this notation, and this is what I'm getting to. This is what we're doing, and this is what we did the first unit, is they switched it to the Roman letter S. That's what this integral is, and you're going from A to B. So this is now a definite integral where you're taking all the sums of all the y values, and the dx is your change in your x. So they changed the delta to d, so it's more like a derivative, and then you're taking all this here. So this stands for the width of the rectangles, and here's the heights, and you're doing the sum of them. And it also makes it nice because this is a smooth curve, and this is has more sharp arrows. So this kind of is a nicer notation saying we're trying to find the area under the curve to find the distance traveled. Okay? So there is the introduction to how you find area under the curves and how we're coming up with using this notation.